Polyhedron is a solid that is bounded by polygons called faces that enclose a single region of space. So looking at the diagram down here, this is a polyhedron because each of its faces are polygons. So like up here would be some type of rectangle, same thing goes for here, and on this side, the bottom would be some kind of rectangle, and then the two faces here would actually be trapezoids. And it's enclosing this region of space inside of the polyhedron. An edge is a line segment formed by the intersection of two faces. So this red segment would be an edge. Back here is an edge. All around here, all of the places where two of the polygons are coming together, those would all be called edges of the polyhedron. A vertex is a point where three or more edges meet. So the vertices would be here, here, back here, up top here, and here, and then the two places down here. So just like we've always thought about vertices, where things come together at a point, we're still referring to those as vertices of now the polyhedron. And just a reminder, a circle is not a polygon. So if you have some kind of three-dimensional figure and one of its faces is a circle, it would not be a polyhedron. With that being said, here are the types of solids that we will look at. The first type would be the polyhedrons, which another way to say the plural of polyhedron is polyhedra. So here we have polyhedrons, and then we also have things that are not polyhedrons. So if it is a polyhedron, then all of its faces are polygons. So all of these faces would be rectangles. All of these faces are either triangles or rectangles, like here on the bottom. These are not polyhedrons because they have faces that are circles, things that are not polygons. So just like I said before, if one of the faces is a circle, it is not a polyhedron. If you're trying to classify a solid, it says of the 5 solids above, the prism and the pyramid are the polyhedra. So this would be a prism and this would be a pyramid. To name a prism or a pyramid, use the shape of the base. So the difference between a prism and a pyramid is that a prism has 2 bases, whereas a pyramid only has 1 base. Looking at the prism first, one thing that students struggle with is identifying which 2 faces are the bases. Some students just automatically assume whatever face the prism is sitting on is automatically one of the bases. However, the bases are going to be 2 congruent polygons that are parallel to each other, meaning they're never going to intersect. Also notice that the faces that are not bases are rectangular in a prism. Again, remembering that the 2 bases that are congruent polygons that are parallel to each other and all other faces are going to be rectangular, that should help you identify what kind of prism that you have, since you name a prism based off of what shape the bases are. Like with prisms, you name a pyramid based on the shape of the base. And remember, a pyramid only has 1 base. Also notice that the faces that are not the base in a pyramid are triangular. So in prisms, the faces that are not the bases are rectangles. In a pyramid, the faces that are not the base are triangular. So again, if your base is a triangle, it's called a triangular prism. If your base is a hexagon, it would be called a hexagonal pyramid. Now let's see some examples. So here's example number 1. Tell whether the solid is a polyhedron. If it is, name it and find the number of faces, vertices, and edges. So here's part A. This would be a polyhedron because all of its faces are polygons. More specifically, this would be a prism because it has 2 bases, but figuring out which 2 are the bases is a little bit tricky for this type of solid because which are the 2 bases? Could it be this side and this side? Could it be the top and the bottom, or the front and the back? But either way, we have 2 bases that are rectangles. So the top and the bottom are rectangles, the 2 sides here are rectangles, and the one in the front and the one in the back are rectangles. So it really doesn't matter which 2 you're qualifying as the bases because they're all rectangles, so this would be a rectangular prism. Next, let's find the number of faces, vertices, and edges. So when we look at the faces, we look at how many polygons there are. So we have the 1 in the front, 2 in the back, 3, 4, 5, 6 faces. The vertices would be all of the points. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 vertices. And the edges would be all of these segments. So we have 1, 2, 3, 4 on top, 5, 6, 7, 8 on the bottom, 9, 10, 11, 12 edges. On to part B. Is this a polyhedron? It would be a polyhedron if all of its faces are polygons. However, we see some circular things happening in here, so automatically I would say this is not a polyhedron. This is actually two spheres cut in half, tacked onto the ends of a cylinder. And now on to part C. We would say this is a polyhedron because all of its faces are polygons. And specifically, this would be a prism because it would have two bases. But once again, just like in part A, it would be hard to figure out which two are the bases since all of them are the same. All of these faces are squares. So it doesn't matter which two you pick out, they will all be squares. So we would call this a square prism, but there really is no such thing as a square prism. A square prism is technically called a cube. So once again, if all of the faces are squares, instead of calling it a square prism, we're just going to call it a cube. Now on to finding the number of faces, vertices, and edges. Since we have technically a rectangular prism in here, since a square is a rectangle, we'll have the same answers as we had in part A, but let's just verify that. So the faces, we have the one in the front, the one in the back, so there's 2, 3, 4, 5, 6 faces. The vertices would be all the points. We have 1, 2, 3, 4, 5, 6, 7, 8. So just like before, 8 vertices. And the edges, you have the 1, 2, 3, 4 in the front, 5, 6, 7, 8 in the back, 9, 10, 11, 12. So 12 edges, just again like we had for the rectangular prism. Speaking of the number of faces, vertices, and edges, that brings us to our next theorem, Theorem 11.5, which is called Euler's theorem. I know this word doesn't look like it should be pronounced as Euler, maybe like Euler's theorem, but it's really pronounced Euler's theorem. It states the number of faces, F, vertices, V, and the edges, E, of a polyhedron are related by the formula F plus V, so the number of faces plus the number of vertices, is equal to the edges plus 2. So looking at our example over here, this has 6 faces, just like we saw in the previous slide, 8 vertices, and 12 edges. So the number of faces plus vertices, so 6 plus 8, which would be 14, is equal to the number of edges, 12, plus 2, which is 14. So you can always figure out the number of faces, vertices, and edges by using F plus V equals E plus 2. Now on to some more terminology. We have regular polyhedra. A polyhedron is regular if all of its faces are congruent regular polygons. So we have 2 examples here. We have a regular convex polyhedron because all of its faces are congruent triangles. But this would be a non-regular concave polyhedron because not all of its faces are the same size or shape, and it also caves in on one side. There's actually 5 regular polyhedrons. They are called platonic solids. So again, this means that we have 5 different kinds of regular polyhedrons where all of the faces are congruent regular polygons. And they're shown down here on the slide. Platonic solids are named by the number of faces that they have. So the first one is called a regular tetrahedron. Tetra means 4. So it is a regular polyhedron with 4 faces, and in this case the faces are regular triangles. Next we have a cube, which is a platonic solid with 6 faces, and in this case all of the faces are squares, regular parallelograms. Next we have regular octahedron. That octa means 8, so that means we have 8 faces that are all regular triangles. Then we have regular dodecahedrons. That means we have 12 faces, and in this case, the faces are regular pentagons. And the last one is a regular icosahedron, which is a regular polyhedron that has 20 faces. And in this case, all 20 faces are regular triangles. So again, we have 5 platonic solids, and platonic solids are named by the number of regular polygons that are the faces of the polyhedron. Example Example number 2, find the number of faces, vertices, and edges of the regular tetrahedron. Check your answer using Euler's theorem. So since it's called a tetrahedron, we know that's 4, but let's just verify that. So you have 1, 2 in the back, 3, and then the base here is 4. So 4 faces. The vertices would be 1, 2, 3, 4. And the edges would be 1, 2, 3, 4, 5, 6 down on the bottom. And Euler's theorem says the number of faces plus the number of vertices is equal to the number of edges plus 2. So let's verify that. We had 4 faces, 4 vertices, and that meant we have 6 edges plus 2. 4 plus 4 is 8. 6 plus 2 is 8, so this checks out with Euler's theorem, so we know that we didn't miss any of the faces, vertices, or edges as we counted them up on the diagram. Next, we have some more terminology. The intersection of a plane and a solid is called a cross-section. In this section, you'll be asked to describe the shape that is formed due to the cross-section. And so the way I think about this is like I'm taking a knife and slicing through the solid, and then what shape is being exposed due to that knife cutting through the solid. So in this case, when this plane, the red area here, slices through the blue pyramid, it would be a triangle that is shown if I took the two pieces apart as I cut through it. We'll see more examples of this in the next slide. So here's example number 3. Describe the shape formed by the intersection of the plane and the closed cylinder. So when I look at part A, I imagine a knife slicing through the cylinder and I'm pulling the two pieces apart, and what would this shape be? So when I pull those apart, since this is a three-dimensional drawing, it kind of looks like an oval, but when you actually look down on it, it wouldn't be an oval that is formed, it would just be a circle. And now looking at part B, this time we're slicing through it vertically. So what would this shape be when I pull the two pieces apart? And in this case, it would be a rectangle. And now looking at part C, we're slicing through the cylinder diagonally. So when I pull the two pieces apart and look down on it, it will actually be an oval. But the mathematical way to say an oval is called an ellipse. And that's it for this section. Make sure you jot down anything you didn't understand that we can cover in class before we move on, and we'll see you then.